thank you. Hopefully everybody online can hear me, and I appreciate people showing up in person. So I'm going to talk about something that I've really been thinking about a lot over the last few years, about sort of how we get out of, what position we're in and how we get out of it. But let me just start out before that by saying that it's always great to be back here at Goddard. I spent 10 tremendous years here. Here's some very old pictures of me and my colleagues, Mark Schoberl in the upper left, in the lower right, Rich Slarsky, both of whom are retired. It's me and Larry Twigg on the softball field, and Paul Newman still has that boyish exuberance, amazingly enough. Anyway, this is a great place, and I'm really always happy to be back here, so thank you very much for the invitation and the opportunity to see so many of my old friends. I start with what I think is really the plot that sets the context for the problem. So this shows 30,000 years of the Earth's history, 20,000 years in the past and 10,000 years into the future. So it starts, I will use a pointer for people in the room, but I'll also try to describe where I'm pointing for people online. It starts if you go back to 17,000 years BC. That's the depth of the last ice age. And then over the next 10,000 years, the climate warmed up. We exited about 10,000 years ago, and we've been enjoying a pretty nice interglacial, very pleasant interglacial, during which human society as we know it evolved. And then you'll notice there's this really weird thing. The pointer is dying. There's this really weird thing that's happening right there. And you might say, what the heck is happening? And it turns out that's the fossil fuel era. So viewed in a geologic scale, the fossil fuel era is going to be this brief spark in humanity's history. Started about 200 years ago, and it's going to end. Maybe it'll end in 20 or 30 years, maybe it'll end in 200 years, but it's going to end soon. And so for all of human existence, there'll only be a very short period where people use fossil fuels. It's when we live. So in some sense, we live in a remarkable period. And you can see, oh, sorry about that. All right, sorry about that. So you wanted me to turn the power to my lavalier mic on. So you can see that it has this profound impact on what on the climate. Now, if you look at how much it's going to warm the climate, it's not that much. Or at least it doesn't sound like that much. 3 degrees Celsius. I mean, 3 degrees Celsius is nothing. You might think. Who cares? It was, it's going to be 10 degrees Celsius cooler tonight than it is today. Winter and summer can be 50 degrees Celsius different. How can that possibly matter? And the short answer is, when we talk about temperature, we're talking about the local temperature. What I'm plotting here is the global temperature. Temperature changes of 3 degrees Celsius and the global average are enormous. And to prove that, note that the last ice age was only 5 degrees Celsius colder than it is today. So think about that. Really think about that for a moment. If you cool the world by 5 degrees Celsius and the global average, you get an ice age. You have thousands of feet of ice over North America and Siberia. Sea levels are 300 feet lower. Ecosystems look completely different. That's 5 degrees. Now, we're going to warm the climate by 3 degrees in this century and maybe the following century. That is an enormous amount of warming. That is going to completely remake the planet. And then the kicker is that once it ends, and my laser pointer's dead. Once it ends and emissions stop, the climate doesn't cool off. It's going to take 100,000 years for the climate to cool off. So the decisions that we're going to make, us and the next generation or two, are going to determine what the climate's like for 100,000 years. Now, people sometimes say, oh, you can't predict the climate. I mean, I don't think anyone here would say that, but on Twitter they would say that. So let me just show you one plot that I find particularly powerful. This is a plot, I've obscured part of it, but Wally Broker published this in 1975, and he said, what's the climate of the next, he made a prediction of what the climate of the next 40 years would look like. And the blue line are the observations and the orange dots are his prediction. Let me just go back. So you can see that when he made the prediction, that was not obvious what was going to happen. And yet, with a little physical intuition and some luck, he was able to nail the temperature. Now, we have a good history of predicting the global average temperature. So we've done that many, many times. Exxon has even done it. So when we show you a plot that looks like this for the future, you should believe it. It's pretty simple physics. It's really not that complicated. Now, you'll see where we are. You are here, I'm here. So we're about a third of the way up this sort of business as usual curve. So we've warmed the climate by about 1 degree. We have maybe 2 more degrees coming. And even with 1 degree, let me say, 1 degree is a lot of warming. Again, people will say, 1 degree, that's nothing. I walk outside, it's 10 degrees warmer. Again, we're talking about the global average. And with 1 degree of warming, we can already see things happening. So this is just a potpourri of headlines that I pulled out. Wildfires, extreme heat events, hurricanes. Now, climate change doesn't cause these things. Climate change doesn't cause hurricanes, or hurricanes before climate change. There'll be hurricanes without climate change. What climate change does is it's a threat multiplier. It's steroids for the weather. So climate change can take a hurricane that would have done some damage, like Harvey, and it can make it far more damaging. It can increase the rainfall. It can increase the wind speed. It can do all of these things. It raises the sea on which the hurricane's riding on. That makes storm surge more damaging. Similarly, it can take a heat wave, which would have been bad, but it adds a few degrees to it. And as I'll talk about in a second, it's nonlinear. So those last few degrees can do a lot of damage. So that actually brings me to this point of nonlinearity. So people often think, in fact, the human brain is really designed for linear thinking. We do really well if I give you a data point here and a data point here, and you will draw a straight line through it. But that's not the way that climate change influences us. Climate change is a much more nonlinear impact. So as an example, people may have seen this. This is an expansion joint on a bridge. So the reason this is here is engineers know, as well as we all do, that things expand and contract when the temperature changes. So if you build a bridge, that's going to be in a range of temperatures. You have to build it so that it can expand and contract. If you don't, it's going to be damaged. So the engineers, when they build it, they say, well, how big of an expansion joint do we need to add? Well, they take their temperature climatology and they say, okay, well, what's the hottest temperature the bridge is going to see? It's this. Let's add a few degrees to be safe. And that's how big they build the bridge. And so what happens is, as the bridge expands in warm temperature, there's no damage, there's no damage, there's no damage, because the expansion joint can accommodate that. And then at some point, the expansion joint closes. And at that point, if it keeps expanding, the bridge is damaged. And this is something that actually happens. You see this. You see bridges actually be closed. And there are lots of these assumptions built into our society. So train tracks are exactly the same way as the bridges. Train tracks expand and contract. And when they build train tracks, they build in expansion joints. And they say, okay, well, this is the range of temperatures that the tracks are going to experience. And so we're going to build enough expansion that it can get that range. And if the temperatures exceed that range, the tracks run each other and they buckle. And you get something called a sun kink, and you can't run the trains. Similarly, cement buckles. The cement buckles, still dead. Does the same thing in Portland during the last heat wave. The insulation around some of the wires got too hot and they melted. And again, these are all assumptions. They built in an assumption of what the hottest temperature they were going to see is. And once it exceeds that hottest temperature, it's damaged. And so what happens is, the way to think about climate damage is you have no damage at all until you hit a threshold. And once you hit a threshold, the damage goes up very rapidly. So let me give you an example that's closer to home for me. This is a house that's near where I grew up. In Meyerland section of Houston, and it's a 5,000 square foot house with a really beautiful landscape. It's clearly designed by an architect. It has a copper chimney. It has a pool. So it's really, really a beautiful house, selling for $86 a square foot. I think that's on there somewhere. Selling incredibly cheaply. And you think, wow, why is it so cheap? Well, it's so cheap because the house has flooded. So if we read along, mid-century modern, home flooded in 2015, and again during Harvey, but not in 2016. That reflects the fact that Houston had 3 500-year floods in a row on consecutive years. And this home would be a great candidate to lift and remodel. So they can lift homes for about $75 a square foot. You can jack it up 6 feet off the ground. And then incredible curb appeal. So that's okay. So let's look at the value of this house over time, because I really want you to think about nonlinearity. Okay, so this is again Zillow data. This is the tax value of the house. The x-axis is year. The y-axis is again the assessed tax value per Zillow. So if we look at the 2000s and into the early 2010s, the house was doing really well. It started out at $400,000, went up in price, went down in the around 2010 in the Great Recession, but then after that it recovered nicely. Value is going up. And so, the people here, they're saying, who cares about climate change? I'm not being affected by climate change. Climate change is a problem for the future. And it's true. They just didn't realize the future was tomorrow. Because what ended up happening to the value of this house is it flooded twice, and nobody wants to buy a house that's flooded. Okay? And the flooding came on suddenly. It wasn't like this was a 30-year process where it flooded a little bit every year. You go from flooding is a binary situation. You have a house that doesn't flood, and you have a house that does flood. There's nothing in between. And when you transition from one state to another, you lose $500,000 of value. Now, I don't know who owned this house. It looked like the original owners who probably built the house in the 60s still owned it from the sales date. I don't really know. But I do know they're a lot poorer today than they were in the mid-2010s. They could have sold this house. They could have paid for their grandkids' college education. They could have gone on a cruise. They could have done anything. Now they can't do that because their house is not worth nearly as much as they thought it was. And so what I always tell people is this you? Are you somebody who's about to get hammered by climate change? Because it's going to be somebody. There are people out there who think climate change is never going to affect me, or climate change is a problem for the future. But they're about to get hammered. There are people out there like that. I hope it's not you, but it could be. And it's important to understand there are these risks that are extremely nonlinear out there. And now, this is a tragedy for the owners of this house, but it's also a tragedy for society. And let me explain how these nonlinearities actually ripple out through society. So imagine you have a neighborhood, and the neighborhood floods. Your house doesn't flood, but a bunch of your neighbors' houses flood. Okay, so the tax base declines. You saw the assessed tax value of the house went down. That's what they base property taxes on. They get fewer property taxes. That means they don't have as much money to spend. So hospitals they can't hire a doctor. They can't fix the roads. They can't hire a science teacher. Schools decay. And you get this social decay. And then nobody wants to live in a place like that. So the people who are rich, who have resources, they move. That further pushes down the tax base. That causes further social decay. That causes more people to move. And this is a feedback loop. It's a social, physical feedback loop, just like we see it in science all the time, except this is a coupled system. And ultimately, what ends up happening is everybody who can move moves. And then the grocery stores leave, and then the banks leave, and the gas stations leave. And the only people left are people who are too poor to leave. And you have a place which is literally unlivable. So I've given you kind of the bad news first. Let me give you sort of my cartoon summary of this. So I think about this as a probability distribution plot. And so you have the outcomes on the x-axis, and then how high it is how likely it is to come. So we look at the outcomes of climate change. This is how basically I would draw it. Sort of this bell curve on the bad side. Now, there are no good outcomes to climate change. Economists have worked on this for a long time, and almost all of them agree that climate change is going to be a net negative. They don't agree on how big a net negative is, and I could talk more about that, but I won't in this talk. But they all agree we're going to be worse off. And so when you think, okay, well, that doesn't look too bad. Maybe I'll end up being close to zero. Well, how close you are to zero is going to be a strong function of how wealthy you are. So Elon Musk, he will be okay. If it gets that bad, he can go to Mars. But then the question is, what about us? So we're not rich. Or it's a bit differently. Globally, we actually are rich. If you have $100,000 of net, if your net wealth is $100,000, you're in the top 1% globally. So a lot of us are very rich globally. We probably don't feel rich. I certainly don't feel rich. You probably don't feel rich. And the answer is nobody really knows how bad it's going to be for people like us. I mean, maybe it won't be that bad. Some people, if your house floods, it's going to be bad. Maybe you'll be lucky the house won't flood. It won't be that bad. Maybe you won't have health impacts from fires that are driven by climate change. You know, we don't really know. But it's a risk. It's a risk that's extremely hard to quantify. Now, what about people who are poor? So the world is full of poor people, and I'm talking about people much poorer than the poorest people in the U.S., people who live on a few dollars a day. But even in the U.S., the poorest people are barely going to get by. Let me violate SciComm 101 here, and I'm going to read you a paragraph out of an article by my friend Jeff Goodell in Rolling Stone about extreme heat in Phoenix. It's really, I mean, I can't tell you, I was blown away when I read this, and so I like to reproduce it and read it to people, even though people tell me never to do that in the talk. Can we survive extreme heat? So on hot days, Juarez, who's this very poor woman who Jeff profiled, her small apartment feels like a cave. Because she has poor credit, her utility has given her a card reader that plugs into an outlet. She has to feed like a jukebox to keep the power on. Juarez turns on her AC only a few hours a day. Still, her electric bill can run $500 a month during the summer, which is more than she pays for rent. She shows me the meter on her card reader. She has $49 worth of credit on it, enough for a few more days of power. And when that runs out, I am in trouble. So when we go back and look at this distribution, people who are poor, they are barely getting by today. They are not going to get by in a world with these nonlinear impacts. They're, you know, if you can barely afford to run air conditioning today, imagine Phoenix is 5 degrees warmer. It's going to be a much less pleasant, a much less livable planet. And so you'll often hear people say, oh, we'll adapt to climate change. And 100% of the cases, the people who say that are rich people. And what we'll adapt to climate change really means is let's normalize suffering. Okay, let me summarize with a quote from William Nordhaus, who won the Nobel Prize in 2019. I think this really, in some sense, summarizes the challenge of climate change. It says, technological change, really fossil fuels, raise humans out of Stone Age living standards. Climate change threatens in the most extreme scenarios to return us economically whence we came. And this is the challenge of fossil fuels. We live lives of unimaginable luxury because of fossil fuels. But if we keep burning them, it could return us back from whence we came. And that's really the challenge. Now, let me just briefly go over other reasons why fossil fuels are terrible. They kill millions of people because of air pollution. So I'm not going to spend too much time talking about it other than, there's been a lot of work done on this. And inevitably, if you ask who the people who suffer the most, it's poor people. It's, the Los Angeles Times ran this article about diesel death zones, about how the places with the worst particulate pollution were by far the poorest place. You see that in Houston, people who lives near the ship channel. It's the poorest people. In addition, fossil fuels are terrible for our national security. So by using fossil fuels whose prices are set on a global market, we allow people like Vladimir Putin and Saudi Arabia to affect our national policies. Putin invaded Ukraine. One of the reasons is he thought the world wouldn't respond because we relied on his fossil fuels too much. Saudi Arabia is actively intervening in our elections to elect someone who will be friendlier to them. So foreign countries should not be allowed to do that. I think most people would agree with that. And let me just show you headlines that will never be written. Texas wind prices skyrocket as energy sector responds to U.S.-Russia tensions. Or Saudi Arabia rejects Biden's plea to increase sunlight. Switching to renewables, I'll talk about renewables in a minute, but switching to them avoids all of these problems. Now, that leads me into the good news. We are living through an energy revolution right now. We have, as I'll show you in a second, we have the tools to solve this problem. We're not solving it because of politics, not because we don't understand it, not because we don't have the technology. And so let me just give you a few more. These are one of the very few plots in this talk, but one of them that I think is really amazing. This is the price of solar energy over the last 10 years or 12 years. So it shows you in 2009, solar energy was $360 per megawatt hour. Today, it's about $35 per megawatt hour. Solar energy has dropped by a factor of 10, dropped 90% in the last decade. Completely unexpected. And the same thing has happened for wind. Wind has dropped 70%. What this means is most people, when I talk to them, they think wind and solar are expensive. And that's because their knowledge is 5 years old. If your knowledge of this is 5 years old, it might as well be 100 years old. This is moving incredibly fast. And so even just a few years ago, wind and solar were not the cheapest energy sources. Now they are. In fact, solar is probably the cheapest energy in the history of mankind. Now, of course, I love this meme. So Spider-Man in the top, I can't remember what's her name. Well, whatever the Peter Parker's girlfriend in Spider-Man is. She says, "Tell me the truth. I'm ready to hear it." And Peter Parker says, "Everyone already knows renewables are intermittent." And she cries. So we know, so this is the thing that people can't get their heads around. The sun goes down at night. I can't tell you how many times I've been on Twitter and I say, we can rebuild our energy infrastructure using mainly renewable energy. It's like, the sun goes down at night. What you going to do then? We know that. So people spent a lot of time understanding how you build a reliable energy system even if the sun goes down at night. So let me explain to you how this gets done. All right, so before I do that, let me give you sort of two terms I'm going to use that if you don't study energy a lot, you may not be familiar with. The first one is what we call nameplate capacity. So this is how much power some energy source, in this case a wind turbine, provides at optimal speeds. So if you see a wind turbine, they'll say that's a 6 megawatt wind turbine. But that's only a 6 megawatt wind turbine when the wind's blowing at a certain speed. If the wind stops, it's a 0 megawatt wind turbine. So the nameplate capacity tells you how much it generates, again, at under optimal conditions. And that leads us to the second one, which is the capacity factor. So the capacity factor is the ratio of the actual amount of power you're getting to the nameplate capacity. And that varies over time. So sometimes you're getting 100% if the wind's blowing at the optimal rate. Other times, if the wind stops, you're getting 0%. And it can vary between there. So this is a plot that I made from a simplified energy model. In fact, it's online. You can go to it, model.energy. And it's a synthetic grid of wind turbines covering the United States. So it doesn't really, this is a very simplified model. I'm just using it as a demonstration. And it shows you how the wind capacity, how the capacity factor varies. So you see there's a big seasonal sinusoid. We actually get the least amount of wind power in the summer in the U.S. We get a lot of wind in the spring and in the fall. At some points, you're getting 70% of your nameplate capacity. Other times, I put the black dot. That's 5.5%. So let's now ask ourselves a question. Let's imagine that we want to supply 100 megawatts to a city. Okay, so the challenge is 100 megawatts. The citizens of the city need 100 megawatts, 24/7, 365. So can you build a wind system that produces that? And the answer is yes. You just have to build a lot of wind. And in fact, how much wind you have to build is set by the minimum capacity factor. If at a minimum, the network is generating 5.5% of its nameplate value, that means you have to build a 1,800 megawatts nameplate of power. It's like 300 big turbines or something. I mean, 100 megawatts is not very much power, just to give you an idea. That's not very much power. It's a small city worth of power. So you can do it. So you actually can build a grid that's run just on wind that can produce 24/7 reliable power. And if you build 1,800 megawatts of wind, nameplate, this is actually how much power you'd have. And you see that at all points, it's above 100 megawatts. And at 1 hour of one day, it's exactly 100 megawatts. That's the 1 hour where the capacity factor is at a minimum, and that determines how much you have to build. Now, you probably see the problem with this approach. You are tremendously overbuilding how much energy you need. In fact, on some hours, you're throwing away a gigawatt of power. You need 100 megawatts, but you've built so much wind because of that one time when your capacity factor is a minimum that you are throwing away enormous amounts of power. In fact, on average, you're generating 600 megawatts of power. So you're throwing away 83% of the power. And so this turns out to be what I would say is not an optimal solution, which is why nobody suggests we do something like this. So let me just give you some numbers that come out of this same model. So qualitatively, these numbers are right, but you have to realize this is not a sophisticated calculation. I'll show you a more sophisticated calculation in a minute. But for natural gas, the cost of a natural gas network would be about $60 a megawatt hour. That's about 6 cents a kilowatt hour. We could build this wind network for $231 per megawatt hour. That's 4 times as expensive. And again, the reason it's so expensive is because we have to overbuild by so much. We're building 18 times as much power, nameplate, as we need. And we're throwing most of that away just because there's these very short periods where the capacity factor goes to 0, and you have to be able to generate power even when the capacity factor is low. All right, so nobody suggests we do 100% wind for this reason. It just wouldn't work very well. But what about wind and solar? So now the beauty of wind and solar is that they tend to be uncorrelated, or at least not strongly correlated. Depends on where you are. But in Texas, for example, they're really not very well correlated at all. You get most of your wind at night. Obviously, you don't get a lot of solar at night. You also get a lot of solar in the summer when wind is not producing very well. And so I'm not going to show you the plots, but I'll just show you that if you build wind and solar, the price comes down a lot. So you've gone from $231 per megawatt hour to $152 per megawatt hour. So you've dropped 30%. And the reason is because wind and solar are not strongly correlated, you don't have to overbuild as much. You see in the last column, I had to build 1,800 megawatts for a wind only, but for wind and solar, I only have to build 1,100 megawatts of wind and 160 megawatts of solar. So because I have to build less, it turns out to be less expensive. But I can still satisfy the power every hour of the day. So we can do this. Obviously, it's a question of cost. All right, so the real reason this is so expensive is because neither wind nor solar are what we call dispatchable. So if you look in the energy literature, you'll hear people talk about dispatchable power. Dispatchable power is power that can be turned on and off at will. Solar and wind are not like that. Either the wind's blowing or it's not. If it's blowing, you got power. If it's not, you're not. But if you have a hydro plant, you can turn that on or off. You just turn it on, let water run through the turbines. If you have a natural gas plant, you just turn the natural gas on and it flows. So it turns out that if you add some dispatchable power, you can get a much cheaper grid. So let me show you what would happen if we look at wind and solar and natural gas together. So now we have sort of, and this is sort of the grid we have today. If you go to Texas, wind, solar, and natural gas actually are the primary energy sources. And what would this look like? Okay, so the minimum cost is 182 megawatts of wind, 130 megawatts of solar, and 83 megawatts of natural gas. And again, we're doing this so we can generate 100 megawatts every minute of every day. And this is actually what it looks like. And what you see is that that most of the time, solar and wind generate most of the power. But when they don't, you can turn the natural gas on, and the natural gas will make up any shortfall. And there's very few spikes that are going above 100 megawatts, which means we're not throwing away very much of the power. So we don't curtail very much of the power in this scenario. And so this scenario is 77% wind and solar and 23% natural gas. So we've already gotten to almost an 80% clean grid. And the beauty of this is much cheaper than 100% natural gas, because natural gas is expensive, and wind and solar are not expensive. And if you're not having to overbuild by huge factors the wind and the solar, then you can end up with a very cheap system. Now, you might be thinking, I can't believe this is so expensive. After all, you have 83 megawatts of natural gas over here. That's almost equal to 100 megawatts up here. How can this be cheaper than that? Plus, you've built all the wind and solar. And you have to understand the economics of natural gas. Natural gas plants are dirt cheap to build. When you buy electricity that's generated by natural gas, almost all of the cost is the natural gas. So in this wind, solar, and natural gas plants, you build a lot of natural gas, but you don't run them very often. And you can do that. You just pay them some money to stand by, and then when you need them, they buy natural gas and they run. You pay them for that. But if you don't need them, they just sit there. And that's actually not that expensive, because natural gas plants are mainly operating expenses. Their capital expenses are very low. And so you can actually build this grid. So this is actually a cheaper grid than an all fossil fuel grid. And you can, if you want, turn the dial. So this bottom line is, again, 77% clean, 23% natural gas. If you wanted 90% clean grid, you just build more wind and solar, but that would push the cost up. And so you could essentially dial whatever you want. And when you get to about 90%, it's about equal to natural gas. So we could generate a 90% clean grid for about the same price as a natural gas grid. All right, so what about wind and solar and batteries? So I'm not going to talk too much about that other than to say batteries are, this is using data that's a couple years old. The price of batteries is plummeting. It's just like the cost of solar. Remember, solar dropped 90% in 10 years. Batteries are in the midst of an identical price drop. So as of a few years ago, replacing natural gas with batteries actually raised the price for two reasons. One, batteries, and the other reason is you need to build more wind and solar because you have to charge the batteries. You don't have to worry about that. So those are two reasons. But very soon, this will be price competitive with this. We will get to 100% clean grid, wind, solar, batteries, for a comparable price as the price of batteries plummets. So, we are there. We are there. We can largely get rid of fossil fuels. Whether it's 80%, 90% clean, we can do that. And we can do that at a price that's not going to increase the cost. Let me just add one thing. People always ask me about nuclear. I'm not going to go over this other than to say, if you want me to talk about nuclear, I'm happy to answer a question. Nuclear is very expensive, and nuclear has the opposite character of natural gas. It's extremely expensive to build, extremely cheap to run. So you can't do what you do with natural gas, which is build it and just leave it on the side and run it when you need it. That's a disaster with nuclear. If you build nuclear, you want to run it 24/7. And so it turns out that it's very hard to fit nuclear into a model like this. But ask me questions, and I can talk more about this later. So I often will talk to audiences and say this, and people just say, they just call bullshit. It's like, bullshit. None of that's right. Wind and solar are expensive. And I say, look at the data. So we can actually look at the retail price, which is the x-axis, paid for. So each dot is a state in the U.S. The x-axis is the retail price. The y-axis is a fraction of energy they get from wind and solar. And you can see there's no correlation. It is not the case that states that have more renewable energy are more expensive. And in fact, the state that has the most renewable energy is Iowa. It's mainly wind, and that has among the cheapest power. And again, this reflects how cheap renewable energy is. Now, renewable energy gets expensive if you try to get to 100%. That's not what we're trying. None of these states are doing that. At most, it's 50%. And so you avoid a lot of the problems of the last 10% or 20% of getting to fully renewable. But this really shows that this is cheap. Renewable energy is cheap. It's really the question of how do you build the system. Now let me just show you one. So everything I've shown you is simplified. Is a simplified model. Let me show you some actual research done by professionals. And I guess I'll point to, this is really one of my favorite studies, this Berkeley 2035 report. There's another one by Net Zero America. And then NREL has, so there's lots of people that have studied with sophisticated models that take into account seasonal cycles, realistic wind, everything you care about. And this is what the Net Zero America. So they did what I talked about, a 90% clean grid. So their plan is to take our existing energy system, shut down all the coal, retain the natural gas, and then build a lot of wind and solar. And then you get all the power from wind and solar, and when it doesn't make enough power, you turn natural gas on. And in that kind of network, you get to a 90% clean grid. And with a 90% clean grid, this blue line is, this is sort of our existing energy structure. If we just do business as usual and we're burning a lot of coal and natural gas, this green line is the 90% clean grid. And you see they cost almost exactly the same. And if you wanted to pay less money, make it an 85% grid or an 80% clean grid. If you make it if you relax out a little bit, the cost goes down. If you make it 95%, cost goes up. So at this point, we can kind of dial the price we want. But they studied this 90% clean grid. And this is just the cost of the energy. If you take into account the health impacts, remember, burning fossil fuels kills millions of people every year. And so this blue line is the cost of our existing energy system if you include the health impacts. This green line is the clean energy system. And the reason it's going down is because over this period they're transitioning away from fossil fuels. And this is really the point where they're 90% clean. So you can see that it's actually much cheaper to society to switch to this 90% clean grid. And I have another plot which I will not show. But I'll just summarize right here. So at the beginning of the talk, I said, pick one of these. Is it climate disaster or climate solution? And the answer is it's really both. So we are on the brink of things rapidly getting worse. And they're rapidly getting worse because, remember, we have all of these assumptions of the climate built into our society, and we're just exiting that range. All of the bridges, all of the water structures, all of the seawalls, everything is designed for a climate that's not going to exist in the next decade or two. So we can expect these to rapidly get worse. It's not going to be linear. The next degree is going to be much, much worse than the last degree. We don't know how bad it's going to be. But for us, it could be really bad. Maybe it won't be that bad. For some people, it's going to be terrible regardless. We can be 100% sure people who are poor are not going to be able to deal well with higher temperatures because they're unable to deal well with what they have today. You can't throw a bunch of new challenges on them. They don't have money to build new water infrastructure or air condition everything. We have the technology to solve this. We know how to largely decarbonize our energy system. There are some challenges, but given, I always talk about the Montreal Protocol and ozone depletion and how fast innovation came once people were properly incentivized. If you look at how fast we phased out ozone depleting substances, it was much faster than people predicted in advance. And I think the same thing's going to be true with energy. In fact, you already see it. You already see innovations rapidly occurring in battery space and long-term storage spaces like this. So it's not a technical problem. It's not a political problem. It's really, it's not a scientific problem. It is a political problem. And, it's one that, as I tell my students, it's really, they've got to work on the solution. I guess we do too. We need to be telling our elected leaders that we want them to fix this. So thanks.
So we have some time for questions. If anybody has a question, please use the microphone because it's being recorded.
So you kind of touched on what I find is my worst case scenario here. Two words that terrify me is environmental refugees. You've got places like Bangladesh that have 200, 300 million people that are going to have to go somewhere. Is India going to take them? I doubt it. China? What kind of ramifications do you see here? Because we're going to have a massive migration, and this is going to cause geopolitical conflict, probably wars, and resource wars on top of it. you think there's a solution before that starts happening, or are we just in big trouble?
Yeah, that's a good question. I 100% agree with you on, one thing I do talk to people about is, you don't like, immigrants in Texas. A lot of people don't. What do you think's going to happen when there's a big drought in Central America? They're gonna come north. Obviously, I almost hate to say this, but if you get the way I've always looked at geoengineering is it's like the airbags in your car. If you really think you're on the brink of something really bad, it's the last page of the playbook. You don't want to do it. So I think that's what I would say if you really get in a worse situation. Otherwise, you just got to start working now to reduce emissions and hope you can do it fast enough to avoid that. Hopefully world institutions can provide enough support that those places don't collapse and people start moving.
Well, geoengineering brings up a new realm of discussion, and the one that bothers me about that is who gets to control the thermostat? Brazil's not going to want what Canada wants. Russia's not going to want what India wants. Again, you have huge conflict.
Yeah, no, you're right. I mean, we've gotten ourselves into a situation that's not optimal. And at this point, it would have been great if we had started on this 30 years ago. But at this point, we have a lot of choices that are not great. And what we should be looking for is what's the least bad choice.
So what is your take on putting a price on carbon? Based on what I've seen here, it's not as important because the price of the renewables are competitive with it. But yet there are still, I was just at a meeting down at the Brookings Institute with all these policy people, and they were talking about putting a price on carbon, and the Europeans are looking at their imports and evaluating the carbon content of what's coming in, and they're saying, well, if the carbon content import is larger than what would be manufactured in Europe, we're going to hit them with a cross-border adjustment.
Yeah.
What is your take on that?
So I think that there's a transition that's going on now based purely on price. So if you look at the Texas energy market, for example, you look at their interconnection grid, people are mainly hooking up wind and solar and batteries at this point. That said, that's not true everywhere. And the place a price on carbon could help is it could really speed up this inevitable economic transition. So I think while the economy is, if you left the economy alone, in 2050, we'd probably be 2/3 renewables, 1/3 fossil fuels. And that's sort of not fast enough. And so a price on carbon can take what would be a sort of a slow transition over 30 years and make it a faster transition over 20 years. It also would encourage innovation. I mean, one thing that everybody agrees on is we need innovation, things like long-term storage. Long-term storage is really going to be important for addressing the intermittency of renewables. And a price on carbon could help that because it would give something that you could actually, that people could use to support the investments in that. So I think there is still a place for price on carbon.
Hey, Eddie, great talk. One of the questions I have, and this is maybe goes a little bit to what you were just answering, is the question of total cost. Energy power plants have to be replaced over time. These are good replacement technologies. So there's an overall cost to this city, this hypothetical city of 100,000 people or whatever. Is it a major incremental cost for this city? And then the second part of that is a lot of people have put, solar cells on their roofs and are turning to electric cars. And the energy usage is going to go up for this hypothetical city. So a couple of factors kind of in this simple model, and I was wondering if you could kind of address cost and growth of energy consumption.
Yeah, so this is a plot that I actually skipped over, and they actually looked at this. They looked at exactly the question I have. This is for a 100% net zero economy, and they looked at the total energy system costs, including things like retiring things that are not completely depreciated. Yeah, you got to pay those people, and so that goes into the cost. And they include things like the fact that, with the amount of electricity, there's actually, there are competing factors. So on the one hand, yes, people have to drive cars. That increases electricity. On the other hand, you may not know, I was shocked to find out, we spend about 6% of our energy mining, refining, and transporting fossil fuels. So that's something that's gone. So you save some energy, you get some energy. Heat pumps versus natural gas, for example, are more than 100% efficient. So that's not a 1 joule for 1 joule swap out. So it turns out that people have done those kinds of calculations of how to electrify the whole economy. And the short answer is this plot, again, I apologize for how small it's the x-axis is year and the y-axis is a percent of GDP spending on energy. And you can see that they have various net zero scenarios. You're paying kind of similar prices historically. Maybe it's a little bit more than the reference cost, which includes some renewables, but not going all the way to 100. And so, you're paying a few percent of GDP. So this is not a back-breaking exercise. And people have done unbelievably sophisticated calculations of the entire energy system. The literature is out there, and it's not going to break the bank. Yeah, REF is business as usual. And that includes some transition renewables. So if you look at what would happen in the absence of any policy, renewables would grow kind of slowly until they're about 70% of power. And at that point, it kind of makes sense to keep the last 30% fossil fuels. If you want to get rid of that last 30%, you need policy, like a carbon tax or something that gets rid of that last 30%.
You mentioned a couple of times that we don't quite know how bad it'll be for us. Curious your take on why we don't know. What's the relative importance of scientific uncertainty versus political uncertainty?
Oh, there are two answers to that. So on one answer is how bad it's going to be is intrinsically a value question. So let me ask you, how much would extinction of polar bears, how much is that worth to you? And the answer is, but for some people, I would feel bad if polar bears went extinct. I think, they call them charismatic megafauna for a reason. They're charismatic. People like bears. So, and I often ask my students, how much would you pay a year to keep polar bears around? It seems like, $10 or $20 is kind of the generic amount. But it's really hard to evaluate non-market goods, things that are not bought and sold in the market. If something's bought and sold in the market, it's pretty easy to value it. The other problem is that we don't really have data for what happens once we have good data for how people react to historical temperature variations. So you can see as the temperature gets warmer, productivity goes down. But we don't have good data for what happens once you get outside the range. And so the economists have basically assumed it's this quadratic equation. And in fact, I have a plot. I have a plot that shows you how little we... So these are what are called damage functions that economists use. So the x-axis is how much global warming you have. The y-axis is reduction in GDP. And they don't even agree on the shape. They don't agree on the magnitude. And if you look at it, Nordhaus, who won the goddamn Nobel Prize, says 5 degrees of warming is like 8% of GDP. That is insane. There's no way you could get an ice age of warming and only reduce GDP by 8%. That is crazy. I think if he were here, he would say, oh, don't extrapolate the numbers that far. But the field of economics has not covered themselves with glory in this problem. I mean, they have not understood the potential upside, or rather the downside of damage. I think in 100 years, my worst fear is that GDP will still be high, but it's because we're building seawalls and we're digging, wells. We're not buying stuff that people want, like cruises or college educations. Everyone's trying to grow food, and everyone's out and back, trying to protect their land but GDP's fine, So it's because that's what we're spending all of our money on. And there are all sorts of other problems with this about how GDP losses are distributed. And, you could wipe it. Here's another example. Africa is a few percent of GDP. So one way to lose just 3% of GDP is to wipe Africa off the map. That would be a few percent of GDP. Now, I think most of us would agree from a value standpoint, that's not a very good that wouldn't be an acceptable outcome. But still, these numbers don't tell you how it's distributed. And so even a small amount, and they just really don't know those things. So we have no idea how bad it's going to be.
Thanks.
Online, we have a couple of things. One is a comment. Peter Parker's girlfriend is named Mary Jane Watson.
Oh, Mary Jane.
Everybody
Yes.
needed to know that.
All right. Yes, Mary Jane.
Then we have a question. For intermittent energy generation from wind and solar, why aren't storage technologies like flywheels, which NASA has researched for lunar energy storage, being seriously considered?
Well, I can't answer that specific question, but I can say there are a lot of people working on storage. The ones you hear most about are obviously batteries, particularly new battery chemistries, like air batteries, open air batteries that use air as one of the constituents. You also hear about hydrogen generation. So while instead of curtailing the energy, use it to run an electrolyzer, you generate hydrogen, you store it in a cavern, and then you pump it out and generate power with hydrogen that way. So there are a lot of people working on it. I don't know about flywheels. I actually have not heard about that. But certainly there are a lot of people working on that. And I think if I were a college graduate these days, I would think seriously about going into batteries or storage technologies. It's like plastics in the graduate, plastics. It's storage.
Another online question. What was the address of the house again? You should check for flood risk designation from First Street on Redfin.
Yeah, I should. I haven't looked at this in a couple of years. I did know it. I do think it's sold. This is probably 3 or 4 years old. I think it did sold. It's 9611 Cedarhurst. And I know exactly where it is. Like I said, I grew up about a mile from there, and it's right next to a bayou. There's a lot of interesting stuff that you can do to evaluate risk. But, the thing about First Street, I will just say this. No one really understands how that works. These climate consultants put these products out, but it's not the same as scientific research in that, reproducible code, it's online. Some of them are better than others, and for all I know, First Street is one of the better ones, but some of them are really opaque.